Welcome back friends to our Induction Motor Complete course in my YouTube channel TechTide Digital Lifestyle, and today in DAY3 we are going to understand the most important topic of induction motors, which is the working principle and the concept of rotating magnetic field, because without this you cannot understand how torque is produced or why the rotor rotates. Let us begin with the basic idea. When a three-phase AC supply is given to the stator windings, alternating currents flow in each phase, and these currents produce magnetic fields. But because the three currents are displaced in time by 120 degrees, the combined effect of these three magnetic fields is that they form one magnetic field which appears to rotate inside the air gap of the motor, and this is called the rotating magnetic field, or RMF. This RMF has almost constant magnitude and rotates at a speed called synchronous speed, which depends only on the supply frequency and the number of poles of the stator, and the formula for synchronous speed is N equals 120 multiplied by frequency divided by number of poles, where frequency is in hertz and poles are the total number of magnetic poles in the stator. For example, if the supply frequency is 50 Hz and the motor has 4 poles, then synchronous speed will be 1500 revolutions per minute. Now this rotating magnetic field cuts the stationary rotor conductors, and according to Faraday's law of electromagnetic induction, whenever a conductor cuts magnetic flux, an EMF is induced in it. So an EMF is induced in the rotor bars, and because the rotor circuit is closed, current starts flowing in the rotor conductors, and once rotor current flows, the rotor itself produces its own magnetic field. Now we have two magnetic fields present in the air gap. One is the stator field, or RMF, and the other is the rotor field, and these two fields interact with each other, producing a force on the rotor conductors according to Lorentz force law, and the direction of this force can be found using Fleming's left-hand rule, and due to this force, torque is produced and the rotor starts rotating in the same direction as the rotating magnetic field. As the rotor starts rotating, its speed increases and approaches the synchronous speed, but very importantly it can never reach exactly synchronous speed, and the reason is simple. If the rotor were to rotate at the same speed as the RMF, then there would be no relative speed between the rotor conductors and the magnetic field, so no flux would be cut, no EMF would be induced, no rotor current would flow, and therefore no torque would be produced, and that is why in practical operation the rotor always runs slightly slower than synchronous speed. The difference between synchronous speed and rotor speed is described by a quantity called slip, which is defined as slip equals synchronous speed minus rotor speed divided by synchronous speed, and slip is usually expressed either as a fraction or in percentage by multiplying by 100, and at standstill when the rotor is not rotating, slip is equal to 1, while at normal running condition slip is very small, usually between 1 to 5% for most induction motors. From ETO and COC exam point of view, you must clearly remember the definition of rotating magnetic field, the working principle of induction motor, the formula for synchronous speed, the concept of slip, and the reason why rotor speed is always less than synchronous speed, because these are very frequently asked in theory as well as short questions. So today in DAY3 we have covered how a three-phase supply creates a rotating magnetic field, how current is induced in the rotor, how torque is produced, the meaning of synchronous speed, and the concept of slip. And in the next lecture we will move to performance parameters and losses in an induction motor. So please like this video, subscribe to the channel TechTide Digital Lifestyle, and continue learning with us in the next part. Thank you.